Hey guys, it's Mike Burns. For the last few weeks, we've been talking about circuits in physics. And basically, I just wanted to make a screencast that would summarize the different types of circuits and how we can calculate different things based on what we see in a diagram. So let's begin. It was the series of times. In a series circuit, the currents of all the individual resistors, or the individual parts, are going to be the same as the total current in the series. So if you had 3 resistors or 3 light bulbs or something, right, the current through them would all be the same in a series. Whereas, as we see here, I sub 1 equals I sub 2 equals I sub 3 equals I sub total. In the same respect, when you have resistors in a series, the total resistance of the series is going to be equal to the sum of the individual resistors, because the current is passing through each of them. As a result, you simply add them to get the total. Now let's look at what this would look like in a diagram. Here we can see 2 light bulbs in a series circuit with 2 batteries. We can also see, using the non-contact ammeter, that the current passing through each light bulb is the same. Here we have a reading of 0.9 amps, here 0.9, and 0.9. This tells us that each of these light bulbs is receiving the same current, which, as you can see, is creating the same brightness for both bulbs. Overall, anywhere along this wire, you're going to get a reading of 0.9 amps, because it's the same, given the fact that this is a series. Now, let's look at a different type of circuit, a parallel circuit. It was the parallelist of times. In a parallel circuit, the currents of the individual branches are going to equal the total current through the parallel portion of the system, or the parallel circuit. So if we had 3 individual branches, we'd see that their currents I sub 1, I sub 2, and I sub 3 equaled the total current. At the same time, if you had 3 different resistors on these branches of the parallel, the total resistance would be equal to the inverse of their sum. So 1 over resistance of the first plus 1 over resistance of the second plus 1 over resistance of the third equals 1 over resistance of the total. This is going to typically give us a lower resistance than if the resistors were in parallel. Now let's take a look at a diagram to see how a parallel system works. So this is our series circuit, as we saw before. Let's see what happens when we expand it and make it a parallel circuit. Alright, so things are about to get a little more complicated now, as we attach an additional branch. Now we can see that we have 2 branches, 2 different portions of a parallel circuit connected together. We have the first branch, comprised of 2 light bulbs, and the second branch, also comprised of 2 light bulbs. Let's see what happens when we look at the amperage passing through each of these portions of the system. So we see that the total, first of all, is equal to 1.8 amps. Let's observe what the total amperage is for a single branch. 0.9. And as we saw before, if we move anywhere along this branch, since the light bulbs are in series, it will be the same, 0.9. Let's check the other branch now. Also 0.9. This tells us that that each branch is drawing the same current from the batteries, which makes sense because each has 2 light bulbs, one here and one here. So these 2 pairs of light bulbs are going to draw the same power because they require the same amount of electricity to create this brightness that they're giving off, which in all 4 cases is the same. Finally, we can see that the branches, 0.9 amps here and 0.9 amps here, add up to the total current of 1.8 amps, as seen, given our rules on the previous page. Now let's see what happens when we mix the 2 together. It was the age of confusion. How do we figure out circuits that have a combination of series and parallel circuits within them? Let's take a look at one now and try and figure it out. So here's our parallel that we had before. Now let's see what happens when it gets a little more complicated. Alright, well, now we are dealing with a much more complicated series. We can see here that we have a lot going on. First, we have our original parallels, right? Here are two light bulbs in series and two light bulbs in series that form their own parallel branch, right? They're in parallel with each other. Then on top of that, that whole thing is in parallel with this crazy outer branch that we have going on. And then within this outer branch, it's all in series except for these two light bulbs, which are parallel to each other. So now let's try and figure out what it looks like if we look at the individual parts of this circuit with the ammeter, because that's going to be really how we figure out if this all still makes sense with what we already figured out. So now I'm just bringing it a little tighter so it's not such a crazy mess on the screen, and then we'll take a look to see if our equations have held true for this now. So let's see if I can zoom back in here. Alright, most of it. So we'll move around as necessary. But for now, we can see that the total amperage right now is 2.31 amps. Alright, so a little weird number, but nonetheless, we'll make it work. So if we look here, we see this part's pulling 1.8 amps. This side is pulling 0.51. 1.8 plus 0.51 is 2.31. So that holds true. Since our branches go parallel, the sum of their currents is equal to the total. Now, let's look and see that in this case, yes, 0.9, 0.9, still holding true. These add up to 1.8. So this part makes perfect sense, right? We know that on this side, each of these light bulbs is getting a current of 0.9 amps. On this other branch, we notice the same, and it makes sense because it adds up to the total on that branch. Now let's look at this other branch that we have. It says 0.51 amps. Let's see how that affects the various light bulbs along it. And with that quick adjustment, we can now see everything on screen. So let's take a look. We have 0.51 amps. So based on our rules, in the series portions of this, 0.51 amps should be the current through each light bulb. So we see 0.51, yes, passes through the first light bulb. Let's skip over this parallel bit for a second and go look over here. We see 0.51 amps. Yes, this is accurate. Same thing on these ones. Then, for these two that are in parallel, let's take a guess. If we have two light bulbs, one here and one here, that are each pulling on the 0.51 amps current in this wire, how is it going to divide between the two? That's right! It is going to divide evenly between the two. 0.26, 0.26. Now, due to a rounding error, that adds up to 0.52 as opposed to 0.51. But nonetheless, you were right. Great job. All right then. And to conclude this screencast, it was the age of understanding. The key here when you're dealing with circuits is to remember everything in this video, and then you'll be able to solve any resistance problem with ease, any matter of current or amperage or ohms or anything like that. Of course, in this video we only discussed the currents, but the same applies if you just use the rules for the resistance that we also mentioned, and you'll be able to solve the problem without any issue. Just remember to look at each individual part of the circuit and realize that it's just a bunch of smaller, easier ones like we started out with, added up together to make it look like it's hard, but bottom line, it's really not that bad. Happy circuitry solving!